Hello everyone, welcome to another lecture in our course on Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are in week 10 now, and this is our last lecture in this course. So we will start with a recap. I made some very complex animations to visualize what happens inside of a neural network, and I hope you enjoyed them. After the recap, we are going to tackle a practical problem using machine learning. First, we will solve this problem using our own algorithm, and then I will show you how you can solve it by using Google's TensorFlow library. In the first part of our course, the most essential concept was that of a derivative of a single variable function. A single variable function has a single input and maps it into a single output. Its derivative gives us a measure of how sensitive is the output to a tiny change of the input. A derivative is a ratio of two algebraically constructed fictitious magnitudes. The value in the denominator is approaching zero, and the value in the numerator is dependent on it. This makes the derivative's value larger than zero, but at the same time smaller than any feasible measurement. From the geometric standpoint, a derivative gives us the slope of the tangent line at any point on the function's graph. If our function has multiple inputs, which is usually the case in computational models, then the concept of a derivative needs to be extended. So what changes is that instead of one, we need to compute multiple derivatives, one in terms of each input. Here, since the function f has two inputs, we need to compute two partial derivatives. The first is the derivative of the output in terms of x, and the second one is the derivative of the output in terms of y. The first value tells us how changing x influences the output to input ratio, and the second one how changing y influences the output to input ratio. If we store all the partial derivatives of our function f in a vector, we call this vector the gradient of the function f. Gradients gives us tangent slopes in terms of all of the inputs. Since the function f has two inputs and could be represented geometrically as a 3D surface, its gradient specifies two slopes of the tangent plane of our surface at any desired point. Here we have a single valued function y of x represented with a green line. If we know the derivative of this function, we can use it to gradually minimize or maximize the function's output. We can start from any input value x on the graph. If we subtract the derivative, multiply by a small number c from the input value x, we will get a new input value x new, which will give us a lower output than the previous x value. If we want to minimize a multi-valued function f, the process is nearly the same. For each input, we subtract the corresponding partial derivative, multiply by a small number c. We get new inputs, x new and y new, and if we multiply them together, the result f will be a lower number than before. After covering derivatives, we introduced the Perceptron model and used it to formalize a decision-making process whether we should go and see a movie or not. Here, our questions were, for example, is it raining outside? And our answers could only be yes or no. We can think of our responses to these questions as the model's data points. Each of our responses is weighted according to its importance and then compared to a threshold value. So if we wanted to enforce a particular decision outcome, given our answers, we need to find a way to change our weights and the threshold. However, Perceptron has some limitations in this regard. Its inputs and its output are all binary. It uses a step function as a decision mechanism, thus it is not a continuous differentiable function, so we cannot use derivatives to steer its variables to achieve our desired output. But we can extend the Perceptron model. By changing the inputs and the output into real numbers and introducing an activation function, we obtain a much more powerful model called an artificial neuron. Here I represented a single artificial neuron as a circuit diagram. The equation below looks quite complicated with all the indexes, but this is only because we are not yet using linear algebra. An artificial neuron is a function of n+1 variables, which means n weights parameterizing n inputs and one bias. To compute the output, we need to multiply all the inputs a with their corresponding weights w, add the bias term, and then pass the resulting sum through the activation function. If we think of a neuron as a function of multiple variables, which it is, it will be a continuous, nonlinear, differentiable function outputting a real number. If we connect multiple artificial neurons together, daisy chaining neurons' outputs to neurons' inputs, we obtain an even more powerful model called an artificial neural network. This network of neurons will remain nonlinear, continuous, and differentiable, but the chaining and layering of neurons will introduce even more degrees of freedom. The biggest challenge of using this model to steer decisions in terms of our data is to compute its gradient. How can we compute partial derivatives in terms of potentially millions of variables organized in hierarchies of different layers? Let's ask a simple question. How could we, for example, compute the partial derivative in terms of the first weight of the first neuron in the first hidden layer of our network? Well, let's first consider an even more straightforward case. Here we have a chain of 4 functions, f, g, h, and k, of a single variable called input. Even in this case, computing the derivative of the output in terms of the input could pose a serious challenge. Luckily, we can use the chain rule of calculus. So the chain rule allows us to represent this complicated derivative as a product of simpler ones. The situation is almost the same when we have a function of multiple variables, except that we need to take into consideration the branching of neurons' outputs. So if we want to compute the partial derivative of the final output in terms of the value z2 of the second layer, we need to take into consideration that the output of that particular neuron feeds into the 2 neurons in the following layer. For that reason, when computing a partial derivative of some value in a network, we need to sum partial derivatives over all paths leading to that value. In this particular case, there are 2 paths that we need to consider. One goes over the first neuron of the layer 3, and the second one goes over the second neuron in the layer 3. Let's define a simple machine learning problem. According to the given distribution of red and blue points in a 2-dimensional plane, we wish to predict the color of any point on this plane. To distinguish between classes of points, our model relies on data. This means that our 6 data points should define a boundary between blue and red points. We know that our artificial neuron is a differentiable function with multiple inputs. The question is, how can we use derivatives to derive the boundary between these 2 classes? What has function minimization to do with learning, and what do we actually minimize with derivatives? And this is where a cost or loss function comes into play. Our data set consists of 6 points, and each one is associated with a red or a blue label. We encode blue points with the number 1, meaning 100% blue, and red points with 0, meaning 0% blue or 100% red. Then we take a single data point and plug it into our neuron or a network. The network outputs a value that you can see on the bottom graph. There will be a distance between the neuron's output and the point's label, which is currently set to 1. Our cost function called mean squared error computes this distance, squares it, and it produces a new output. This new final output, called cost or a loss, tells us how bad our network is doing. And since we want our network to perform well, then we use derivatives to minimize this cost. We compute partial derivatives of the cost, which is our final output, in terms of weights and biases, which are our variables. Updating the values for weights and biases will iteratively decrease the gap between the output and the label. As the total cost for all the data points gets smaller, the boundary between different classes of points becomes more and more accurate. You might be wondering, is it possible to visualize the cost of our neural network? The answer is yes, but this can only be done in a very unique case when we have a single neuron with a single input. Since we only have a single input, we will have a single weight and a single bias. And the only thing we can use this neuron in terms of classification is to classify points on a line, like we have here on this example. To do machine learning in this particular case, we do not even need to compute the derivatives. We can just use a graphing calculator to derive what should be the values for our weights and for our bias. Let's see how we can do this. We are now in an open source software called Geogebra, which can be used as a graphing calculator, but it has also many more uses. Here on the center, we have a 3D space visualized, and we assigned our axes as following. So the first axis, or the x-axis, we will display weights on it. Y-axis, we will display biases on it. And the z-axis, we will display the cost or the loss for our inputs, which are the data points and the current selection of weights and biases. Here we have our data points. So we have 6 data points with coordinates -5, -2, 0, 2, 4, and 9. And each of them has a corresponding label. So zeros means blue and ones they mean red. What we don't have yet is a sigmoid function. So let's define a sigmoid function first. So sigmoid of x will be equal to 1 divided by 1 plus, in parentheses, exponential function of -x, like we did it in Python. Here is the sigmoid function visualized. But actually we do not need to visualize this function. So I will turn it off. How can we then display the geometry of the cost function for our first data point? So as you can see, if I wanted to take the output for our first data point, it is defined in this table as A1. So if I type A1 here, I will get a value -5. If I type A2, I will get -2. If I type A6, I will get our last data point's output. Okay, and if I want the label of the first data point, instead of A1, I can just say B1. Yeah. Okay, so how do we then compute the output of our neuron? So we need to multiply the weight by our activation, or the first data point's output, and then add the bias, take the sigmoid of all of that, subtract the label, and then square it to get the mean squared error for this point. So let's do that. So A1 will be our first data point. We multiply it by the weight. And as I said before, weight will be represented by the x-axis. So when I use x, this always means weight. So this times weight plus y, which is our bias, we get a plane in 2 dimensions. But now we need to put sigmoid activation to this, so we will say sigmoid and put this in parentheses, and we get some kind of a surface which is bounded between 0 and 1. We know that this is what sigmoid actually does. It squishes all the inputs in the z direction between 0 and 1. But we are not done yet. We need to subtract then b1, which is going to be the label, and square this whole thing. The geometry of our single data point has changed a little bit. Okay, what else can we do? Well, since this is a blue point, let's just display this surface as blue. So we will display it. So if I now make a point on this surface, what does this point tell us? First, let me show you the values of this point. As you can see, where the point is now, its weight value is 3,15, its bias value is 1.38, and its cost for this selection of weights and biases is 0. So if I now move this point on this surface, we will come to a point where the cost will actually be 1, which is the maximum cost. And then we can also come to a place where the cost will be between 0 and 1. And if we go here to the valley, then the cost will be 0. So what we want for this point is that the cost, that its cost, is equal to 0. So we want to minimize the cost. And these are the weights and biases that minimize the cost, as long as we are in this valley. All right, let's delete the point, and let's put the second data point. I will just momentarily turn this off so it doesn't confuse us, and I will just copy this whole formula. I'll copy it, and I will then paste it. So this will be our second data point, so let's change it from A1 to A2, and from B1 to B2. This is our second data point. As you can see, it has a little bit different geometry than our first data point. And this is also a blue point, so let's change its color. Okay. The geometry is very similar. Again, if we make a point here, we want to select a point which will give us the value of the cost axis to be equal to 0. Let's add all the data points. I will just do it quickly. I will also change their colors respectively. Okay, what we have now is 6 surfaces. All have a slightly different geometry because all of them has slightly different input value. But what are we actually interested in? So we need to find a point which eventually will minimize cost for all of them together. So how can we do this? Let me first close these points. What we can do is we can add these functions together. As you can see, these are multivariable functions, a, b, c, d, e, and f. So let's add them. A plus b plus c plus d plus e plus f. When we add them, we get a new surface. And what we are interested in is to find a combination of weights and biases that will lead to the smallest loss or cost on this surface. So if I create now a point on this surface, and let's display its values, we are interested to find the combination of weights and biases which will minimize the cost for all the data points. As you can see, as I move this point, the cost goes up and down. Let's just make another point to illustrate this better. I'll create another point, B, and its x-coordinate will be 0, which means the weight will be 0, and the bias will be 0, and it will have the z-coordinate of our point A, so it will have the same cost. So now, as I move the point A along the surface, you will see that the point B will indicate what is the cost for this particular combination of weights and biases. We are interested to find a place where this cost is relatively low. Let me zoom out a little bit. As you can see, there is a combination of weights and biases that we can choose that completely minimizes the cost, so makes the cost equal to 0. And now we just need to pick the values of these weights and biases. So here we have our data points, or 6 data points, and they're all ranging from the value of -5 to 9. The question is, what would happen if I create a continuous variable, for example p, and p can take the range from -5 to 5, and I can just move the slider to take any of these values. If I now replace the output of our data points with this continuous output, what label will this value p give me if I multiply it with our weights and biases and put it through the sigmoid function? So there's one way to find out. So I have the value p, I multiply it by the current value of our weight, which is 3.27. How do I access this value? Well, this is equal to x-coordinate of the point A. Then I add the bias, which is the y-coordinate of the point A. This is the point A, by the way. And then I put this all through the sigmoid function. So this value here will be a prediction of the label for the current value of p. So as you can see, if p is -5, the prediction is 0, which means this is a blue point. And as I move it, as you can see that this value started changing. It's still equal to 0 for the value of -7, which is understandable. And then as I move it, now the value of p goes somewhere in between. And this is the boundary. So if p is somewhere around 1,2, then we are on the boundary between blue and red points. So there is a huge uncertainty. We do not know is it blue or red. But as soon as we pass this value of 1.2, we are now certain that this is actually a red point because the label is 1. As you can see now, for this continuous variable p, we are able to correctly predict the label. But if I now move the point A somewhere else where the cost is higher, as you can see here, the cost is quite high, now the prediction, I'm supposing, is not going to be good. As you can see, for the value of -5, I should be expecting the label 0, but I actually get the label 1. And if I move p to be 5, I would expect the label to be 1 or red, but that's not the case. I have the opposite value. Again, I can move A somewhere else. Here, again, the cost is around 3. As you can see, still, the prediction is not really correct. If I now have the p at 5, it tells me that it's somewhere on the boundary between blue and red, which is not correct. We obviously know that if point is around 5, it should be 1. But again, how do I fix this? I just move the point A to the value where the cost is very low, and my prediction should be correct. So for the -5 it's 0, and for the +5 is 1. And all the values in between gives you correct prediction as well. However, it is important to keep into consideration that this is the only case where we can actually visualize the cost function as a surface in three-dimensional space. Visualizing the cost function in our example makes it obvious where the lowest cost is and which values to pick for the weights and for the bias. How can we use derivatives here to reach the value with low-cost values? First, we would pick weights and biases randomly, which would give us the point A, which for example has the cost or loss 4,92. First, we compute the partial derivative of the cost in terms of the weight, and then we compute a partial derivative of the cost in terms of the bias. As we already know, a derivative gives us the slope of a tangent line. Here, since we have two derivatives, we will have two tangent lines and two slopes. One tangent is in a vertical plane, which is parallel with the plane that contains the weight axis, and the second tangent is in a vertical plane parallel with the plane containing the label axis. If we subtract the derivatives multiplied by a small number from the weight and bias values, this moves our point downhill and lowers the cost. From this new position, we would again compute the derivatives and get the slopes of the tangent lines. When we update the weight and the bias, we go further down, lowering the cost. Again, we repeat this procedure. And we repeat it until we reach the point for which the cost is close to 0. At this stage, the learning is complete and we can distinguish between red and blue points. A great thing about using derivatives is that we do not actually need visualizations. We can rest assured that as long as we pick the step size adequately and we can compute the gradient, we will eventually minimize the cost in our network. Treating weights and biases as individual elements helped us to understand the necessary details of how our neural network works. Eventually, however, we needed to abstract from this low-level picture. Once you know the details, it is better to think about the model in terms of larger structures and operations of these larger structures. In the lecture 7, we introduced linear algebra to help us achieve this. First, we learned about vectors, which are the objects that have meaning in both geometric and algebraic points of view, and they could be treated accordingly. In computer science, we can use vectors as data structures that can store multiple values in a single object. Each new value introduces a new dimension and more degrees of freedom in terms of vectors' direction and length. Then we learned about matrices, which are mathematical objects uniquely arranging numbers in a rectangular structure of rows and columns. In linear algebra, matrices are used to encode spatial transformations, manipulating the space itself and, of course, all the vectors in it. As you can see, a multiplication of all the points on the screen by a 2x2 square matrix transforms them in a very unique way. depending on what numbers we put in our rows and columns, we can rotate the space, scale it, squish it, flip it, or all of this at the same time. What remains invariant to a matrix transformation is that the coordinate origin remains fixed, and the grid lines that you can see on the screen, they remain parallel and equally spaced. In the lecture 8, we encoded a neural network using vectors and matrices. We used operations defined on vectors and matrices to compute the forward and the backward pass. As you can see on the slide, to compute all the activations of the layer 2 at once, we applied the sigmoid activation to the matrix product of all the weights of the layer 2 with all the activations of the layer 1, to which we then added all the biases of the layer 2. This made the formulas much more concise and elegant. But what I wish to clarify here is the meaning of the weight matrix in terms of spatial transformations. The square matrix on the left is a 2x2 matrix. It will transform any point in two-dimensional space into another point in two-dimensional space. In the middle, we have a 3x3 square matrix. This matrix will transform any point in three-dimensional space into another point in three-dimensional space. But what about the matrix on the right? It is not square. How does this matrix transform the space? I will try to visualize this and much more in our next example. In this example, we have a 4-layer neural network. This network has 2 neurons in the layer 1, it has 3 neurons in the layer 2, it has 3 neurons as well in the layer 3, and in the last output layer, it has 2 neurons. But what about weights and biases? Well, since the layer 2 has 3 neurons and the layer before it has 2 neurons, this means we will have in total 6 weights. And these 6 weights are organized in 3 rows because the layer 3 has 3 neurons, and it is organized in 2 columns because the layer before it has 2 neurons. What about biases? Well, since the layer 2 has 3 neurons, it will also have 3 biases, and each of the bias values is represented within the neuron here. That's how I decided to do it. As you can see, the value is 0 for the biases. Okay, what about layer 3? Well, it is very similar. It has 3 neurons, and the layer before it has 3 neurons, therefore we will have 9 weights organized in this 3x3 square matrix. And we also have 3 biases. What about our last layer? Well, we have 2 neurons in the last layer and 3 neurons in the previous layer. Therefore, we will have 6 weights organized in 2 rows and 3 columns. Layer 4 will also have 2 biases corresponding to 2 neurons in the output layer. Our input layer has 2 neurons, and we could visualize these 2 neurons as a pair of coordinates. For example, we could think of the output of the first neuron as x coordinates and the output of the second neuron as y coordinates. And now if I move my point in this two-dimensional space, you can see the readout of my coordinates in this space here. So here you can see the x coordinates, and here you see the y coordinates of my cursor. What are these lines here? So we have here a red line, which is our unit basis vector I hat, and the green line is j hat. And then here in 3D spaces we have also the blue line, which corresponds to k hat. They're all 1 unit of magnitude. Okay, now as I move the mouse here on the plane, you can see that there are some yellow points in the other 3 drawings, and that they somehow correspond to the same motion. So I'm circling in an anti-clockwise direction around the origin, and this is also happening in all 4 drawings. So what is actually going on here? Well, what is happening is actually matrix multiplication and matrix addition. So we start from our first layer, which encodes 2 points within a single 2D vector, and then we multiply this 2D vector by this 3 times 2 matrix here. And what this matrix actually does is transforms 2D space into 3D space. So if we multiply a 2D vector by it, we get a 3D vector that you can see represented in this space. So if a matrix has 2 columns, this means that it takes 2-dimensional vectors, and if the matrix has 3 rows, it means that it transforms these vectors into 3-dimensional vectors. Yeah? Then to this 3-dimensional vector, the result of matrix multiplication, we add a three-dimensional vector of our bias terms, and then we get a point in three-dimensional space here. Here we take this 3D point, which is the output of the layer 2, or the activation of the layer 2, and multiply it by this square matrix. As you can see, this is a 3 by 3 identity matrix, which means that this matrix actually does not change the space. But in principle, what 3 by 3 matrix does is change 3D vectors into 3D vectors. Yeah? And then to this 3D vector, which is the result of matrix multiplication, we add a three-dimensional bias vector and get a point in three-dimensional space. Finally, we take this three-dimensional vector from here and multiply it by this 2 by 3 matrix. Yeah? Because this matrix has 3 columns, this means that as an input it multiplies 3D vectors, and because it has 2 rows, it means that it turns these 3D vectors back into 2D vectors that you can see here. So the output of matrix multiplication is a 2D vector, and then to it we add another 2D vector of our biases, and we end up with a vector in 2D space. But somehow you can see that there is a correspondence between what I'm doing in my input space with what I'm getting as a result in my output space. Well, this is due to the carefully placed values within our weights and biases. As you can see, all the bias values are 0, and the matrix values are either 1s or 0s. So there is a very specific pattern that I follow here to get this particular mapping. Okay, so what happens if I now change the numbers in our vectors and in our matrices? Well, let's see. If I change our biases, if I change the first bias, we are actually translating the space in the red direction. If I change the second bias, I'm actually translating the space into the green direction. And if I'm moving or changing the third bias, I'm actually translating the space in the z direction. Yeah, as you can see here. And another thing to observe is that since I do this translation in the second layer then affects the third layer. So if I move something in layer 2, then this affects layer 3. But if I do something in layer 3, this does not affect back to layer 2 because the connection goes from left to right. So if I do something in layer 3, this actually only affects the layer 3 and 4. And finally, if I do something in layer 4, this only affects that layer. Okay, so we now know what biases do. And what would weights do in this case? What happens if I change the values in the matrix? Well, the first column of this matrix tells us where I hat will land in the 3D space, and the second column will tell us where the j hat lands in the 3D space. So by manipulating these numbers, I can scale the space or rotate it or whatnot. So for example, if I want to shrink the space, I will take this coordinate where I hat lands and I would shrink it, for example, to 0, 5, and where j hat lands, I will shrink this coordinate to 0, 5, and now our space is more dense, so it's shrunk. But if I make it larger, then we can expand it. And I can do the same thing here in the layer 3. Shrink it as much as I want, or expand it. Yeah? What happens if I move these other numbers? Well, it doesn't really matter what happens exactly, so you do not need to know what exactly happens, you just need to see what is the outcome of moving these things. You can see that I'm actually rotating the space in different directions around different axes, yeah? Also, if I do it here, then I can further rotate it, which has, of course, outcomes in the layer 4, as you can see. And then I can move it around, and also I can also rotate it, squish it, stretch it in our final layer. Yeah. So the interesting thing to notice now, if I now move my cursor in the input space, you see now I'm rotating it around the origin, this corresponds to a completely different movement in our output space. Yeah. So our points end up in completely different place. Let's reset the matrix and weights values back to their original values. So what we are missing here, what else does a neural network have that we do not have here yet? Well, it does not have an activation function. As you know, in each of our neurons, we have an activation function, for example, sigmoid. So let's now apply sigmoid to each of our neurons. I can do it here by clicking on this button. Well, what sigmoid does, what it did here, what you can see, is that sigmoid squishes its input in an output which is between 0 and 1 and does it in all dimensions. So as you can see, the sigmoid has squished our whole 2D input space into a 3D box here, whose all sides are only 1 unit long. Yeah? So as we know, sigmoid of 0 is 0.5, so you will not be surprised to realize that the coordinate origin, which we marked here, that has coordinates 0 and 0, will end up in the center of the space in the next layer. So at the coordinate 0.5, 0.5, 0.5. When we apply sigmoid to this space here in the second layer, sigmoid squishes it further in the next layer. Yeah? As you can see, it gets even smaller, because now input space is only 1 unit high, tall, and wide. Finally, in the last layer, our input space is even further shrunk, and now it takes only a small portion of the space between the unit vectors. Now when I move the yellow point in the input space, its movement in the output space is much more restricted, as you can notice. And again, I can ask what happens if I now change our weights and biases. Well, first neuron will still translate the space in the red direction, second neuron will translate it in the green direction, and the third bias will translate it in the z direction. And the same will happen also in the layer 3 and in the layer 4. But the bigger effect you will see when I start changing the values in our matrices. So if I change the matrices, you can see now that the transformation of the space that I'm currently doing is completely nonlinear. Because sigmoid is a nonlinear function, so the spaces that we get are completely unexpected and nonlinear. So we cannot really predict what will happen when we change some of these values. We can get really unexpected results here. So what we start with and what we end up here in layer 4, we cannot really predict by just changing these numbers. And the nice thing is that we do not even have to do this. So derivative will do this for us, as you will see a little bit later. So if I now move my point in the input space, the resulting values in the output space could be completely unexpected. So I cannot predict if I move a point in the input space where it will end up in the output space. Yeah? And now if I click randomize here, this will randomly initialize weights and biases, and I will get a different spatial configuration every time I do this. And this is what we do in our code too when we implement a neural network. Okay, now we understand the spatial transformation aspect of neural networks. How about what derivatives do and what is learning about? Well, so far there has been no learning because we do not have any data yet. And because our output layer has 2 neurons, and we are using mean square error as our cost function, we can only use this architecture to classify between 2 classes of points, for example, red points and green points. If we wanted more classes, then our output layer needs more neurons, thus we would need more dimensions in the output layer, and we will do this just a little bit later. Okay, in our 3 weight matrices that we have here, and in our 3 bias vectors that we have here, we have in total 29 parameters that we can freely change. Yeah? And because of that, we will have also the same number of partial derivatives that can change these 29 numbers in order to minimize the output of our cost function, so our cost or our loss. And since we cannot really visualize our cost as geometry because we have too many dimensions, we can only represent it as a number. And I represented it here in this rectangle. So if this rectangle gets filled with color, this means that the cost is larger, and if this shrinks to the left, this means that cost gets smaller and smaller. But because we do not have data yet, then the cost does not really exist. But this will of course change as soon as I add some data points. But what would then the cost be here? If I move now my cursor in the input space, you will see that I get a yellow point on the right in the output space. Let's now concentrate on this yellow point in the output space and try to define what would be the cost of this point. Yeah? Well, if this is a red point, then the cost will be the shortest distance of this point to the red axis, and then squared, plus the horizontal distance of this point to the tip of the i-hat squared. So this will give us the cost. And how can we minimize this cost? Well, we want this point, if it's a red point, to get as close as possible to the tip of the i-hat. If it is closer to the tip of the i-hat, the cost will get smaller and smaller. And if it is further away from the tip of i-hat, the cost for this data point will increase more and more. It is the same situation if this point was green. So if it is a green point, if it gets closer to the tip of the j-hat, the cost will decrease. And since now it is, for example, very far from the j-hat, the cost will be significant for this data point here. Okay, now let's try adding some points and see what will actually happen. Please be attentive to the image on the right and then the total cost when I now add a red point. Yeah? So, as soon as I now click and add a red point, the cost quickly jumps up and then starts decreasing as the whole space gets moved towards the tip of the i-hat. So as the point gets closer to its target, which is the tip of the i-hat, the cost gets smaller and smaller. And now look at the weight matrices and the bias vectors now. They have changed from what they have been in the beginning. And now the whole space is kind of pretty close to the i-hat. And now because of that, if I add more points here, there will be no additional cost to our classification. Because the whole space is close to the i-hat, therefore all of these points in my input space, everything in the input space, will be very close to the tip of the i-hat. But what happens if I add a green point? Well, as soon as I do this, the space starts to change. Green points, they need to get close to the tip of the j-hat. So the space starts stretching to accommodate for this. The space stretches in a way so that red points go to the tip of the i-hat and the green points go to the tip of the j-hat. And as this is happening, the cost gets lower and lower. And now we can also see a color gradient between these two classes of points. And this gradient represents the boundary between them. So you see the boundary here. When I'm on the boundary, this corresponds to the point in the output space which is kind of equally far away from both axes. So they should be somewhere here in the middle. And now if I randomize our weights and biases, then the training will start from scratch from these new conditions for the new weights and biases. You should take into consideration one thing here. Some initial values for weights and biases will make the network easier to train, and some initial conditions will make it harder to train, which is why we always tune our neural network. And here I can also change the speed of training for our neural network so that the animation appears faster. As you can see now, when I randomize our weights and biases, you can see that the network quickly classifies between red and blue points. Okay, now I will remove all the points, reset everything, and I'm interested to see how does this network perform with more complicated datasets. So let's try something like this. As you can see, this arrangement of the inputs is not really a problem for our neural network. It classifies them relatively quickly. So if I click randomize, it will do it from a different starting conditions. As you can see here, this is not a very big problem. Sometimes, as you can see, like now, the initial conditions were not that good. So we have some significant cost here. So we should probably reinitialize our weights and biases. Let's change the speed. Or maybe we should just randomize. Let's try one more configuration of our data points. I will again reset everything, and now I will try to put them in a circular arrangement. Some other classification algorithms would have a big problem classifying this thing. but not our neural network. Our neural network does this very easily. As you can see, no problem. Also, you need to keep in mind that this particular network is relatively limited because we want to be able to visualize what's going on, therefore it has maximum 3 neurons per layer. But we will address this later. What if we had 3 possible classes of points? Well, since we are using the mean square error cost function, our final layer needs to have 3 neurons, which corresponds to 3-dimensional space that you can see here. Now, if we add some red points, they will be pushed towards the I hat. If we add some green points, they will be pushed towards J hat. And if we add some blue points, they will be pushed towards K hat, as you can see on the animation. So everything stays the same except the number of neurons in the final layer. And because of that, we can have 3 classes of points. This particular network, as you can see, can easily separate this particular arrangement of data points. And it could also do more complex arrangements. For example, let's try to make 3 circles as our data. I will now increase the speed of training and see if the network can do it. As you can see, yeah, it can. It easily separated all of our input points. Let's click randomize and see if it can do it from different initial conditions. As you can see, no problem. So it can separate relatively complex arrangement of data inputs, but again it has limits because we have very few neurons, maximum 3 per layer. Let's try to put more neurons. Now our second layer has 6 neurons. And obviously we cannot visualize 6-dimensional space. So because of that, it has 6 outputs, and I'm only displaying the first 3 outputs as a 3-dimensional space. And these 3 outputs here I'm not able to represent because it is impossible. Yeah? So if I now change the values in the first 3 rows here, as you can see, I'm affecting this space. I'm translating it in X, Y, and Z directions, actually red, green, and blue directions. Yeah, and I can also change the 3 rows of the matrix, and I will be affecting this space. The question is, what will happen if I modify the rows that we cannot visualize? So if I try to modify these values, well, the interesting thing is that in the picture below, this will not do anything. So this will not affect the 3-dimensional space below, because simply this belongs to the 4th dimension, 5th dimension, and 6th dimension. So this thing here cannot change, also if I move these numbers here. But definitely changing something in these non-visualizable dimensions will have an effect of transforming the next layer, so the layer 3. As you can see, layer 3 is depending on the outputs or the activations of the previous layer 2, therefore this matrix has 6 times 3, 18 elements. So if I, for example, move the 4th bias, you can see that I'm definitely affecting something in the layer 3, or 5th, or 6th. So the interesting thing here is that since now we have more elements at our disposal within these values, we can transform the 3D space, which comes after our high-dimensional space, in much more crazy ways than we were able to do it before. And because of this particular architecture that we are using could be much more potent in classifying our data points. Let's try it out. Let's try some more complex arrangements. For example, I can put some red points here, green points here, and blue points here. As you can see, cost is quite high at the moment, but if I speed up the training, let's see if it can actually do it. As you can see, no problem. Networks is easily able to distinguish between these 3 classes of points. Let's add more complexity to it. Let's add some red points here and green points here. Well, right now, the training has been already finished for the previous situation, so let's randomize our weights and biases to start from new initial conditions. As you can see, our network is doing pretty well, concerning that we still do not have many neurons in our layers, and that the arrangement of our input data is quite complex. Let's try another initial conditions. Well, it looks like it's definitely getting there. Well, although we cannot really understand why are things happening in the way that they are happening in a neural network by looking at this animation, you can clearly see what the outcome of classification is. So our space, no matter how many dimensions it has, gets transformed by changing our weights and biases such that in the final layer, points get pushed as close as possible towards their targets. So the red points get pushed towards their target, which is I hat, green points get pushed towards their target, which is j hat, and the blue points get pushed towards their target, which is k hat. You have learned a lot in this course, and with everything you have learned so far, I really hope that this animation will be a cherry on the top in your understanding of neural networks, as it was for me. Now, let's tackle a practical machine learning problem. We will feed a lot of labeled handwritten digits to our neural network, and the network should learn to recognize them. Then, when we give it an unseen image of a digit, it should be able to accurately predict what it represents. We will work with a dataset called MNIST, containing 70,000 grayscale images of handwritten digits, 28 by 28 pixels each. And on the screen, you can only see a very small fraction of it. Let's take a closer look at the dataset. We have our data points, which are scans of handwritten digits written by many people. There are 70,000 instances of 10 possible digits. To each of the data points, there is an associated label attached defining what this data point stands for. Here we have a single data point, and you can see that it is a low-resolution image. So let's see what this image consists of. If we subdivide the image to expose the pixels, we can see that it is actually a 28 by 28 pixel image. There are actually 784 pixels in total. And let's now try to see what the pixel values are. Each pixel on this image is defined by only a single value, and this single value represents the pixel's brightness. And brightness is set in a range from 0 to 255. On this image, I visualize the pixels with brightness 0 as white pixels, and pixels with brightness 255 as black. Gray values on this image are in the spectrum between 0 and 255. And some programs interpret these values differently. They could, for example, interpret 0 brightness as black and 255 brightness as white. This really depends on the convention used in this visualization library of a specific programming language. But in machine learning, we do not really have to care about visualization conventions, because we are primarily concerned with the numbers that describe the pixels. So the main question here is, how can we encode this bunch of numbers as a single data point? So we will do what we always did. We will store all the values into a column vector. But how do we do this? Well, we will break the image into a line of pixels. We can simply start from the first row, taking values from left to right, until we reach the last number in the final row. After doing this, we now have an ordered list of 784 numbers, ranging from 0 to 255. We just need to organize them in a single vector that has 784 rows and a single column. How will this shape our neural network architecture? Well, our input layer is a column vector with 784 values. Therefore, our input layer needs to have 784 neurons. Our output layer needs to encode probabilities of 10 different digits, from 0 to 9. Thus, it will have 10 neurons. And for the hidden layer, we can freely choose how many hidden layers we want to have and how many neurons per layer. Here, I decided to have only one hidden layer consisting of 100 neurons. You are of course free to experiment with any number of layers or neurons in them and see what you get. Now, let's learn some basics of how the datasets are organized in machine learning. We have 70,000 data points in total, but we will not use them all for training. We will split them in 3 sets. We have a training set, validation set, and testing set. A training set is a part of the dataset that is used only to train the neural network or to tweak its weights and biases. And so far we have only been using a single dataset to train our model. We did not use these separate sets. And now we will use all 3 of them. On the right, we have a testing set. What is a testing set? Well, testing set contains of data points that are not part of our training dataset. These data points are never used for training. They're used afterwards to test the prediction quality of our neural network. If our model generalizes well, then it should be able to classify the previously unseen data, not only the data it knows. If our model accurately classifies the training set, but does much worse on the testing set, this means that the network is overfitting to the training set. It means it is biased towards it. This brings us to the validation set. Its primary role is to prevent overfitting and reduce bias. In the process, we start by training our neural network on the training set, but we will check the accuracy on both the training set and on the validation set. And the accuracy on both sets should go hand in hand for some time. But the longer we train, the training set will get better and the validation set will not get better. And this is the indicator that the network is starting to overfit on the training set. It starts to memorize unimportant features of the training set, and these are the features that do not generalize well to our problem. And the second role of the validation set is to tweak the meta parameters of our neural network or test different models to improve the prediction quality. So how do we split our data? Well, our training set should contain most of the data, so we will assign it 50,000 data points. Our validation set will have 10,000 data points, and our training set will have the remaining 10,000 data points. And now, let's do this example in Python. Okay, let's first start by loading our libraries, and then what it says here is that practically, since we will be using our own code for the neural network, and we will be also using TensorFlow, then we can take the MNIST dataset from the TensorFlow database repository. And because most of the people will, I assume, using Google Colab, then this will be automatically pre-installed for you. And if you plan to use TensorFlow on your own computer, well, then you will get this database too. So it is a win-win for all users. So let's first import TensorFlow STF. And then from tensorflow.keras.datasets, we will import MNIST. And then on the MNIST, we can run the function called loadData, which will load this dataset into our variable dataset. And if you do it for the first time, you will see that there will be some loading process involved. And since I already did it, it's instant. And now let's see how this dataset is organized. Well, we need to unpack this dataset into 4 further variables, into training data, training labels, validation data, and validation labels. And this is the way how we unpack datasets by convention. So this is the convention that you can use on multiple datasets that you will see. Okay, now we have these 4 variables. What it asks me is to check the length or shape of our training and validation data and labels. And because shape also gives you the length, I can just check the shape. So train data, I will type shape, and then you see that you have 60,000 matrices containing 28 times 28 numbers. So matrix of the size 28 times 28, and we have 60,000 of them. Okay, then training labels, let's check the shape. We have 60,000 numbers, which are our labels, so numbers from 0 to 9. Let's check our validation data. our validation data has a shape 10,000 times 28 times 88, which means 10,000 images. And our validation labels has 10,000 labels, 10,000 numbers representing labels. Okay, now it says, since this data set does not have a testing set, as you can see here, only training validation, create one from the training set. Of course, because training set has 60,000, we will take 10,000 and put it into the testing set. So take the last 10,000 data points and put it into variables test data and test labels. And then remove these points from the training set. Okay, of course, this means that since it will have 60,000 points, you don't want to have duplicates in the testing sets, since this would then defeat the purpose of making a testing set. So let's do it. So we take the training data and we take the last 10,000 points. And then we take the training labels and take the last 10,000 points. We will assign this to test data and we will assign this to test labels. And then we need to just make sure that our test, that our training data has 50,000 points. We need to take these points off from the training data and training labels. So we'll say train data equals train data, only first 50,000 points. And for the train labels, we need to do the same. So train labels, only the first 50,000. All right. It says print the shape of the testing set. Let's first check the shape of the training set. It is 50,000. Oh, this is good. And then test data. It says 10,000 points. That's fine. And test labels. 10,000 points. That's fine. Now it says exploring the MNIST dataset. Print the shape of the first training data point. Well, first data point will be train data. And the first point will be with the index 0. Yeah, you can see it's a bunch of numbers and its shape should be 28 by 28. So, and then the following function visualizes the matrix of numbers. So this matrix, 28 by 28 matrix, it visualizes it as an image. Visualize some other data points. Well, let's first visualize the 0th data point, or the first one. You can see it's number 5. And then let's try some other. Yeah, as you can see, as I change the index, I can now check 51st data point in this data set, which is a 3. Now it says for the selected training data point, print the corresponding label. Well, this is training data. Now I need to check training label with the same index. Index is 50. And as expected, the label is 3. So 3 matches 3. And if I say 5 and 5, the label matches the data. Now it says print the labels of the first 100 training data points. So training labels, how do I do that? Well, I can just use the column and say first 100 from 0 to 100. And this gives me all the first 100 labels. Now it says print the values of the 14th row of the first training data point. So training data, this is the first point, 0, yeah. It has 28 rows. Let's take the content of the 14th row. First we index the rows, then columns. So I can just say 14th row. Actually, 14th row would be from 0 to 13, so I will take 13 here, yeah. And you can see there are 28 values in this first row, yeah. Now it says print the values of the 8th column of the first data point. Well, I take the first data point, and then I need to go through all the rows. I want this value from all the rows, but from the 8th column, which is a column with the index 7. If I do this, I get the 8th column, which again has 28 numbers. Now it says find the maximum value in our data set in order to normalize the values. So the maximum will be, for example, train data maximum. The maximum is 255, as you know, and the minimum will be 0. So we can use this to actually normalize the data. And now it says normalize the values of all data sets between 0 and 1. Okay, so we need to have training data, we need to have validation data, and we need to have test data equals. We are going to divide all of this data by 255, because if we divide something in a range from 0 to 255 by 225, then we get something in a range from 0 to 1. So we'll simply divide this with 255 and by 255 and by 255. Okay, now it says, again, print the values of the 14th row of the first training data point. I can just copy paste this. Let's see if something has changed. Well, it has. You can see here we have some values, and here our values are between 0 and 1. Okay, now it says print the shape of the first data point in the training set. So first data point is training data, and then this is the first data point, and its shape is 28 by 28. Now it says reshape this data point into a column vector and store it in a variable dp. So this is the point. How do we reshape it? Well, there's a command reshape, and we need to reshape it into a column vector. So what would be the new shape? Well, it should be 28 by 28. Well, we can use a calculator to compute what is 28 by 28, or we can just say reshape it into 28 times 28, and this should work as well. Okay, and store it in a variable dp. So dp equals this. Okay, now it says what is the shape of the vector stored in the variable dp? Well, that's easy. dp.shape. But the problem is this is not a column vector. Column vector has one column, and here we do not have a one column. So we need to do this a little bit differently. We will say reshape into a shape 28 by 28 for the first dimension and comma 1. Now we will have the adequate shape, which is 784 rows and 1 column. Now it says reshape all the data as column vectors. Okay, let's do that. So we have training data, we have validation data, and we have testing data. So how do we do this? Well, we can use Lisp comprehensions that we learned to do last time. So dp reshape for dp in training data. Again here, dp reshape 784,1 for dp in validation data, and dp reshape 784,1 for dp in test data. Okay, and we should then store this as column vectors, but maybe it's better that we make an NumPy array of this. So np array, because it's faster, array and np array. And now we will store training data. We will overwrite the training data with this reshaped training data. Validation data, we will overwrite it, and the test data, we will overwrite it with the reshaped, well, test data. Okay, done. Now it says print the shape of our training data. Well, training data dot shape now tells us that we have 50,000 column vectors which have 784 rows and a single column, which means this works. Okay, now it says using our own neural network for classification. The first part is, as you know, converting the labels of the MNIST dataset. And for this purpose, we can use the function convert label that we defined before. So it's the same function as we used it before. Okay, now it says convert the label of the first data point in the training set. So train, not data anymore, train labels. And the first data point is train label 0, which is 5. Yeah. So if we use convert label and then convert this train label 0, this will give us something which has 10 rows and a single column, and 0, 1, 2, 3, 4, 5, and where it should, the sixth element will be equal to 1. And sixth element, since we start counting from 0, is number 5, which is this. Yeah. So this will be for the 0, this will be for the 1, this will be for the 2, and so on and so forth. And now it says convert all the label sets into NumPy arrays, train labels new, validation labels new, and test labels new. Okay, so what do we need to do? We have train labels, we have validation labels, and we have test labels. Again, we will use list comprehensions. L for L in train labels. So now what we need to do is convert label L for L in train labels. Now I can copy this, put it here, here, so convert label L for L in validation labels and convert label L for L in test labels. And then we need to overwrite, actually we do not overwrite our train labels, validation labels, and test labels, because you do not have to convert this if you use TensorFlow, it does it for you automatically. We need to put this in our variables, training labels new, validation labels new, and test labels new. Okay, and it might be better to make NumPy array out of this, so NP array will do this, NP array, NP array. Okay, now it says print the shape of our new training labels. So let's try first our old training labels. Shape, so it's 50,000 numbers, and now train labels new should be 50,000 column vectors which have 10 rows, which is correct. Okay, now I have some changes that I implemented in the algorithm that we have used, but they are very, very small changes, and you will be able to understand them. So only two changes are important. First one is when we initialize weights, what we do now is we divide each weight by the square root of the number of activations in the previous layer. And we do this because this makes weight values smaller for the layer which is after the input layer. And why do we do this? Well, we do this because our input layer has 784 activations, which would make weights in the following layer, which has 100 neurons, way, way too large. If you use our normal values between, for example, negative 1,5 and 1,5, they will be too large. So we are minimizing them. Yeah. So where is this in the code? Well, it is here. Yeah. So this is what we do. We divide it by the square root of the number of activations of the last layer. This is the only change. This just helps makes training more efficient. And another change is that we are now using mini batches. Yeah. If we used online training, then it will be too slow if we did one data point after another. But if you did batch training, then we would have to train on 50,000 data points at once. And this would be impossible. We will not have enough memory to do this. And if you want to see how I implemented mini batches, then you should see the other document called Appendix 1, Creating Mini Batches for Neural Network Training. And there I explain step by step how do we create mini batches. And the whole idea is that I take our training data and training labels and zip them into a single object. Like here, I'm zipping here labels and numbers in a single object. And then what I do is I reshuffle these objects so that the labels stay together with their data points. And then from this shuffled data set, I carve out some smaller pieces that you can see here. So for example, my mini batch here has 3 elements. So I'm creating from 13 elements. I'm creating 5 batches here. Yeah. So if you want to know more, check out this document, Appendix 1. So where is this implemented in our code? Well, it is here. I create mini batches in this one line of code, and then instead of going through the whole data set, I'm going through each of the batches in our mini batches instead of going through our whole data set. So these are only 2 lines of code which are improved. Everything else is the same. But in order to use mini batches, as I told you, we need to zip together training data and training labels. We need to zip together validation data and validation labels, and we need to zip together testing data and testing labels to use within our own algorithm. So I do this with this line of code. Then let's initialize our sigmoid and a way to evaluate the accuracy. And now, as you can see, the sizes of our neural network is 784. This is the input layer, 100 neurons in the hidden layer, and 10 output neurons in the output layer. And we will train it with 8 epochs, and the step size will be equal to 3. And mini batch length will be 10, which means we will train 10 by 10 data points. And now let's just run this. Of course, since we have 50,000 data points and they are high dimensional data points, this will be much slower than it used to be before. But I will still show you first in real time, and then I will speed it up. So this is in real time training. As you can see, already in epoch 1, we are getting pretty high accuracy here. 93 points on the training set and 93,57 on the validation set, which is quite good. As you can see, total cost goes down on each additional epoch. And this is the real-time training speed of our neural network, which we implemented ourselves and which is the most basic elementary case of a neural network that you can produce. It has no special engineering and optimization tricks that TensorFlow and PyTorch have, for example. My computer is getting heated up, so you hear some noise. 6th epoch. And the last epoch. Okay, done. As you can see, on the training set, we have a very high accuracy, which is 97.8%, but on the validation set, it is not as high. This means that the network has just starting to overfit somewhere around here, but still, I don't want to now tune this model. I just want to test it on the testing data set. So now I take the same procedure, this evaluate accuracy, on our testing set. And in the testing set are the data points that this network has never seen before, completely different points. And this should tell us how good our network actually generalizes its task. If I run this, it tells us that on the testing set we have prediction accuracy of 96.62%, which is not bad at all, considering that this is our own model. And now we can plot, for example, the wrong predictions. Let's plot 50 first wrong predictions of our model. Let's see what we did, what the model failed to recognize. As you can see, our model predicted here 9, but the label is actually 4. But as you can see, this is kind of relatively similar to 9. Okay. This, it predicted 7, but is actually 1. Here it predicted 3, but it's actually 2. But look at some other points. For example, here prediction is 6, but the label is actually 0. Yeah, this can be kind of close to 6. Or here the actual label is 9, but it predicted 0. So you tell me, is this 0 or 9? See some other points. Yeah, is this really 7 or 9? It's kind of hard to tell. Computer said it's 7, but the person who wrote it says 9. As you can see, these are kind of difficult. Some of these cases are quite difficult to actually recognize, but these are the cases that our computer actually got wrong. All right, and now let's use TensorFlow and its Keras library, which is the library which makes machine learning simpler because it makes it modular layer by layer. You do not have to really write code as we wrote it here. You can just say what layers you want to have and how do you want them organized. Let's first try to recreate our particular model by using TensorFlow Keras. So let's see what do we have here. Well, what do we have is we create a model with this function. We create a sequential model, which means layer by layer. Yeah. And then this is the input layer, which has the shape 784 times 1. Yeah. And then we have a dense layer, which means this is just our normal layer. This is the only kind of layer that we know. This is the layer which has certain number of neurons, in this case 100, which are fully connected to each other. So each layer is fully connected to the layer which comes after it and before it. Yeah. And the activation is the sigmoid, so it's the same activation that we used. And then finally the output layer has 10 outputs, and again has sigmoid activation. Then we have a part where we compile our model. So to compile, this is practically to tell it how to derive the partial derivatives. And we tell it to derive partial derivatives by using stochastic gradient descent. And this is exactly the model which we have been using this whole time. It's called stochastic gradient descent. This is the most basic optimization method of computing partial derivatives. And you know everything about this method. You implemented it. Yeah. The learning rate will be 3,0, the same as for us. And the loss function will be mean squared error, exactly the same as we had. And the metrics will be exactly the same which we had, which is accuracy, telling you how accurate the prediction is. Except that this matrix is a little bit differently implemented in TensorFlow. I cannot now implement within TensorFlow so easily my own accuracy. It's doable, but it's a little bit advanced. And finally, to run this model, I just say fit this training data to these training labels. And for the validation data, I use our validation data set and our validation labels new. Yeah? Because we are recreating our own model in TensorFlow, we are using our own labels. Yeah? The ones that we converted into 10 row, 1 column vectors. Yeah? And we will again use 8 epochs like we did before. Okay, and now you see the training again in real time. You can see that the training is a little bit faster than ours, which is to be expected because this is quite optimized to run or the maximum amount of hardware you have on your cores and on your GPU. I'm doing this on my laptop, so I have no hardware acceleration. I do not have an NVIDIA card, but if you have an NVIDIA card, if you're doing this on Linux or on Windows, this could be up to 20 times faster if you run it on a GPU than on a CPU. But as you can see here, it's not particularly slow, and it's already done. And as you can see, the validation accuracy was around 95% here, yeah? And if we test it on our testing dataset, we get the final accuracy of 95.72%, which is a little bit worse than our own model, surprisingly. But it's kind of pretty similar, yeah? In our model we had 96.62%, and here we have 95.72%. But of course, how TensorFlow calculates the accuracy is not exactly the same, so it's not completely compatible with our model. Yeah? And now, important thing to tell you is that the way how we did classification with neural networks is not the way how you would do it in practice, is not the way how you would do it if you enroll to a machine learning course and if engineers teach you this course. Because the way how I implemented it with mean squared error and with just stochastic gradient descent, this is the most elementary way to do it and to understand all the steps which take place in our model. But if you want to do it more seriously, then you need to see, is the mean squared error really the best cost function for classification? And it turns out it's not. There is a better cost function when you want to classify things, which is called binary cross entropy. And the other question is stochastic gradient descent the optimal method to finding derivatives? Well, it is not. There are a little bit better methods to do it, which are, again, just a variation of stochastic gradient descent, but with some engineering tricks built in. Why didn't I teach you this? Well, because, for example, binary cross entropy or categorical cross entropy is something that you would need to understand the information theory to understand what is going on there. And also, as an optimizer, we do not any longer use stochastic gradient descent, but Adam. And Adam is an optimizer, which is an improved stochastic gradient descent with many engineering tricks embedded so that the solution converges faster, that there is less space for error, and all of this. Again, this is not necessary to understand how neural networks work, but this would be the next step. So when you enroll now to a more advanced course, they will tell you which metrics to use for which kind of problems, which optimizers to use for different tasks, and which cost functions to use. But you already know which are the basics, and this is the most important. You will very easily pick up these latter things. Okay, now let's see what would be the recommended TensorFlow parameters to solve this problem. We would again have a sequential model. We will have our input shape, the same. We'll have again a dense layer. I put 128 neurons. Activation will be ReLU, which is again a different activation function. It's not like sigmoid, it's a little bit different. But again, if you know how to compute the forward pass on ReLU, and you can find this online, and if you know how to find the derivative of ReLU, which is even simpler than of sigmoid, then for you this doesn't change things very much. It's just an activation function, and you can swap it, you can have a different one. And the good thing about TensorFlow is that it's kind of modular, so that you can use very different activation functions, different optimizing algorithms, and different cost functions. You can just specify which one you want. We have a dropout layer here, which is just, again, a trick which reduces the overfitting in the training set. And again, we have the same output. And here we have, again, an optimizer. Again, we are using Adam. We are using sparse categorical cross entropy for classification. And we are plugging the same training labels and training data, but we are now putting our original validation data and validation labels, because it is not necessary to convert the labels if you are actually using TensorFlow. So let's just run this. As you can see, again, it is faster than what we are able to implement, which is, again, not a big surprise, since this is professionally done library used for real-world machine learning problems. It is actually a little bit slower than the previous one, but because we have 128 layers in the neurons in the hidden layer instead of 100 as we had before, but still it is a reasonable speed. As you can see, the accuracy on the training set is now very high, 98.25%. And finally, let's test this model on our testing data set. We get that it got an accuracy of 97.9%, so almost 98%, which is quite an improvement to our 96.62. So when you add all of these tricks, all of this advanced optimization, you get 2% better prediction, which is still significant, but it is not day and night difference. So even with the model that we can do ourselves, and we know all the steps in the process, we can do pretty well, which is very good to know. We have now completed a full circle, and I'm confident that you have an excellent understanding of how neural networks work. And you're also now quite prepared to go further in terms of learning and application. If you would like to continue on a more pragmatic route, I can highly recommend Francois Chollet's book, Deep Learning in Python. He is, by the way, the creator of the Keras library in TensorFlow, so you will be in excellent hands. Also, you will be surprised how readable this book and many other books will be after finishing this course. Before we finish, I just wanted to give you a little bit more thoughts and advices on the topic. First of all, you might remember this slide from the lecture 3 when we talked about perceptrons. What we showed is that you can take a single perceptron, pick the right weight and the right bias, and use it to implement an AND gate. And an AND gate, it is a universal logic gate, meaning that any other gate can be represented with it. And if you implement this gate in hardware, you can build a general purpose computer and implement any computation. So from this particular perspective, you can think of weights and biases of a perceptron network as something similar to machine code. By carefully specifying the values for the weights and for the biases, you can write a particular program to solve some problem. And this is a process which is quite similar to how regular computer programming works. And as you have seen, neural networks are a much more powerful extension of a perceptron network. They rely on derivatives to tweak the weights and biases of the network, in order to solve the problem that you have specified. So you start by saying what you want to have at the end. And then the algorithm, by using calculus, somehow magically, and you know how now, derives the right values of weights and biases. So the writing of a program that solves the problem is something that happens automatically here. For this reason, I would say that neural networks are an inverse of programming. You specify the desired outcome, and the model delivers the code by mimicking the consistency of the data that you have provided. And this code, of course, is not a typical programming code that we work with every day. This code is meaningless and it's unreadable for us humans. It is beyond logic, and the circuits that it creates are beyond logical circuits in computers. So paradoxically, by giving up on understanding the meaning of this code, we can solve problems that we cannot solve by writing the program ourselves by using our programming constructs. And this is pretty significant, philosophically, if you ask me. I also have to mention something else which is quite important. You have seen that neural networks rely entirely on data to produce a probabilistic outcome. And this introduces challenges on so many levels. As you have seen in the animations, a neural network will bend its high-dimensional space in inconceivable ways just to give you the result you want. If you say that some digit is 0, the neural network will turn the whole world around to confirm that anything like it is also 0. Therefore, our neural network reproduces what you want to have. If your outcome was, hypothetically speaking, to prove some theory, a neural network with an adequate dataset would turn the solution space around in most inconceivable ways just to ensure that what you want to show to be true is actually consistent. So your theory itself could be entirely false and it could be completely fake, but the neural network would find a way to support its consistency in terms of the data. So a neural network does not uncover any truth, it rather produces a truth at any cost. And this is potentially something very dangerous if it is misused and if it's not really well understood by people. And this is one more reason why I insist on learning the basics in this course. Another important and extremely challenging thing is data. Well, in supervised machine learning, data is used to define the so-called ground truth. For example, a drawing of a digit 1 is taken to be truthful to its label. But you have seen some written digits in our MNIST dataset which are quite unrecognizable. They are somewhere in between. So what guarantees that the data actually matches the label, except the subjective authority? So let me give you a more vivid example. Imagine now that some government started encoding human beings into data vectors. These vectors are taken to be the ground truth. And let's say that we wanted to predict whether a person is a criminal or not based on its many characteristics. For example, height, weight, eye color, education, average income, or any physical or measurable trait that you can imagine. Then you label these people in binary. Some people committed crimes and some haven't. These are two labels. Then you train your model on this dataset and you want to predict whether some person outside of the dataset is a potential criminal or not. What will you get in this case? Well, a neural network will do exactly what you asked it to do. It will definitely mark some people as potential criminals, and it will mark some people not as potential criminals. And if a particular cluster of people in your dataset have committed a crime, then everyone alike will be marked as a potential criminal. So the neural network has no choice but to reproduce what you want to have, which is in this case your way of establishing the ground truth by labeling people in a way that you're labeling them. So if we implemented this in a system of a governance, well, some people would never have any chance but to be what this label says about them. So the conditions in which the labeling arose could never be changed or questioned, and systemic problems will be completely ignored because this is not something which a neural network trained in this way can do. So this would be an ultimate tyrannical authoritarian system that you can imagine. If you have seen the latest season of Westworld, then you will have a very vivid idea of what I'm talking about here. So we need to be extremely careful about what we actually do with our powerful models. And even in amazing applications such as self-driving cars, where the labels could be, for example, good driving and bad driving, where good driving is defined as driving that leads to fewer accidents, which is something you can measure, there are still serious challenges. For example, an autonomous vehicle will eventually be put in place to decide who potentially lives and who dies in an uncertain, dangerous road situation. And not even to mention that to even train these models in open traffic, we need to put human drivers at risk. So ultimately, there is no free lunch here. Everything comes with a price, so it is of highest importance, in my opinion, to be aware of these aspects and to be responsible for what you do with these remarkably powerful models. And this is another reason why I always insist on learning the basics first, because these models are not merely our tools of the trade that you somehow just download from the internet and use it to solve your problems. They are not merely products that you should use, as companies would like you to believe. These models are the intellectual challenge of our times. So know them intimately, think about them, and be responsible for what you create. Okay, this was a long and a challenging ride. Thank you very much for following this course. I enjoyed very much teaching it, and I hope that you enjoyed it too, and that you learned something valuable. I wish you nothing but the very best in your future learning and in your career. Goodbye.